following program is brought to you by Caltech.
Our next speaker is Professor Jason Wright. Jason received his bachelor's degree from Boston University and his PhD in astrophysics from UC Berkeley. He's now an astronomy professor at Penn State University. Jason is going to tell us more about the search for exoplanets.
All right. Well, I'd like to segue from Eric's nice broad perspective and historical introduction to exoplanets and what we know about them, to perhaps a more technical talk about what we have found in terms of the broader context of all of the exoplanets and how we have discovered all of these planets. So I'm going to talk about diversity in two dimensions here. The first is a diversity of detection methods. There's not just one way to find an exoplanet. We have at least 5 successful methods now. So I'll briefly go over the timing method, which was the first successful method, the wobble or radial velocity method, which is the method that has discovered most of the exoplanets we know of, at least until most of the Kepler candidates are confirmed. I'll talk about microlensing, which is a way that we can find distant exoplanets, but perhaps discover them in great numbers. And direct imaging. Often when we think of discovering a new planet, we imagine that astronomers pointed the telescope and had really high magnification and took a picture of this planet. That's not how most of them are found. We don't have pictures for most of them, but there are a few for which we do, and that's another field that's growing rapidly. And I'll briefly mention transits, only briefly because we'll hear much more about those in the later talks, especially in the context of Kepler. The second axis is the diversity of the planets we've detected. Eric touched on this a bit. Talk about how we have this great diversity of orbital properties that we've detected among all of the known planets. So I'll try to put some of the transit detections we'll hear about later in context. The mass of the star is a way that astronomers can think of the different kinds of stars around which we can look for planets. It's one of the fundamental parameters. Around almost every kind of star for which we've searched for planets, we have found planets. So they seem to be really ubiquitous no matter what sort of star you're looking at. The mass of the planet is one of its most fundamental parameters. We find planets of essentially all masses that we can detect, from many times the mass of Jupiter to just a little bit larger than the Earth, and that's only because we haven't quite gotten down that far yet. And the size of the planet, which has a lot to do with the mass of the planet, but for transiting planets we can measure their size, and it turns out that the size doesn't always depend on the mass of the planet, which reflects composition. What we're learning is that planets have a variety of composition. So in addition to the planets in our own solar system, we're finding a great variety of planets outside our solar system, which is keeping us all busy. So we'll start with the timing method. The timing method is a way of finding planets around other stars. It was first used for the pulsar planets. Alex Volstron, also at Penn State, found 3 extraordinary low-mass objects around this pulsar. This is still an extraordinary and superlative discovery. These are still the lowest mass planets known outside the solar system, and we don't know of anything else like them. So even though they were the first ones discovered, we've never seen other small planets around pulsars since then. So no one's really sure what to make of these. The timing method depends on having a nice clock. A pulsar is a wonderful clock. This dead stellar remnant spins around, and it sends perfectly timed radio pulses at the Earth. And when a planet goes around the pulsar, it pulls on the pulsar, and those pulse arrival times are perturbed very slightly. And from those perturbations, you can infer the presence of planets around the pulsar. In principle, this technique can work for any sort of pulsating star or binary system. And so this technique can be applied to other stars as well. The most prolific method to date is sometimes called the Wobble Method. The idea behind the Wobble Method is that when a planet goes around the star, it's doing so because the star is pulling on it with the force of gravity. And Newton tells us that for every force, such as the star pulling on the planet, there's an equal and opposite force of the planet pulling on the star. And so, yes, the planet is going around the star, but in a small way, proportional to the mass ratio, the star is also sort of going around the planet. And it's this very small motion that betrays the existence of the orbiting planet. To give you a sense of scale, this is a very subtle effect. If you imagine Jupiter going around the sun in a circle, the sun also tries to do a little circle, in a sense, around Jupiter. The speed at which it goes around that circle is about 12 meters per second. So that's a little faster than an Olympic sprinter. And it takes this circuit once every 12 years, which is Jupiter's orbital period. And that's the biggest effect on our sun. So if you were on another star system looking at our solar system and trying to detect planets, you would have to notice that the sun had moved at about 12 meters per second and changed direction over the course of a decade. There are two ways to attempt to detect this wobble. The most straightforward is to try and actually see the star moving on the sky. You look at the background stars that are not moving, and some foreground star is just making this slight wobble, again, every 12 years, back and forth. It turns out that that's a very difficult way to detect planets, and people have tried it for a very long time, and so far it has not successfully discovered a new planet. Very technically challenging. The more successful method has involved the radial velocity of the planet, that is not looking for its motion across the sky, but watching its motion towards us and away from us through the Doppler effect. This is the same effect that makes the pitch of a siren change or a car engine. As it's moving towards you, it's higher pitched. It goes past, the pitch drops very suddenly. So we look for the Doppler effect of the light coming from the star. And to do this, we need to use an astronomical instrument called a spectrograph to disperse the starlight into its component colors. This is a schematic of the Hamilton spectrograph at Lick Observatory, which was used to discover some of the first exoplanets known outside the solar system. The starlight comes in from the telescope, bounces off of a series of mirrors, gratings, and prisms, which, just as any prism will with white light, disperses the light into all of the colors of the rainbow twice, into two different dimensions, which we then collect onto a CCD detector, not unlike the detectors you might have in a camera phone, for instance. This is a schematic of what that dispersed spectrum looks like. The red light falls here, and as you go by, the wavelength, the color of the light, is very subtly changing because we've dispersed the light out so much. And we go from red to orange, and you just read it like a book, yellow, green, down to purple. Each of these dark bands along the way is a color that is essentially missing from the starlight. These dark bands represent chemical components of the star's atmosphere and always occur at the same color. What we're looking for in the Doppler shift is for these missing colors to move, to change their color. As the Doppler shift, when the star is moving towards us, moves all of these missing colors towards the blue or towards the red when it's moving away. This shift is extremely small. Like I said, we're talking about 12 meters per second. If our CCD is 4,000 pixels across, which it is, then we are attempting to notice these lines moving by 1/1000th of a pixel. It's a very challenging measurement, but we do it quite well these days. The next method of detection that I'll mention is microlensing. Microlensing is sort of a completely different way of going about looking for planets. With the other methods, you look at a star and you ask yourself, can I see a planet going around that star? With microlensing, you look at different stars and you wait for stars with planets to come along and reveal themselves to you. This is the idea. Some distant star, the source star, shines and sends its light out in all directions so we can come collect it at Earth. If along the way it happens to encounter an intermediate star, which we call the lens star, Einstein's general theory of relativity says that the light will be focused by that star's gravity. And if the alignment is perfect, that focusing will occur here on Earth. And the source star will briefly appear brighter as the foreground lens star passes in front of it through its normal motion through space. When it passes in front, we will see for a few days this background star get brighter. So we look at thousands and thousands of stars waiting for this kind of an event, because when it happens, we can detect whether the intermediate star, which we might not be even able to see, has a planet, because the planet too will cause a brief brightening of the background star. So by monitoring thousands of background stars, we can detect a few intermediate stars, some of which might have a low mass planet that also does a lensing event. It's a very powerful method of detecting low mass planets in great numbers if you can look at sufficient numbers of stars. The next method is direct imaging, and this is the one that we all really want to see work really well. When you see a picture of the Earth from space, or a picture of Jupiter from space, what you're seeing is sunlight reflected off of the surface of the planet. So you're seeing reflected light from the planet. We would love to take an image of a planet in reflected light from its own star so we could see what's on the surface. That, again, is probably future technology decades hence in some space mission. However, when planets are very young and they've just formed, they can be very hot. And so they can glow very brightly in the infrared. The next problem is that they can be very close to their parent stars. They are much dimmer than their star, no matter how hot they are. So trying to see a very faint object next to a very bright star is very challenging. So it helps if the planet is orbiting at a very large orbital distance from the star so that there's enough separation. So if you're looking around nearby stars where the separation looks big, for distant planets and young planets, you have a chance. And so astronomers build specialized instruments called coronagraphs, which can attempt to subtract the light of the bright star and see a young, hot, glowing planet sitting next to it. Two of the most dramatic examples of this technique I'll show here. The first is the star Fomalhaut. This is a picture of the star Fomalhaut. The Hubble Space Telescope took this image with a coronagraph, and the coronagraph has masked out the star. So there should be a huge bright star swamping everything out here, but the coronagraph has created this black spot. It's also subtracted out a lot of the light in the wings that you would normally see here, but it's done it imperfectly. So these streaks that you see are actually incompletely removed starlight from the star. This ring around here turns out to be real, and that's a ring of dust around the star. And you can't quite see it here, so they've blown it up in this inset. There's a dot inside that ring, or yeah, just inside that ring. And that dot moved from 2004 to 2006. That's a planet orbiting this star, directly imaged, and you can actually see its orbital motion going around Fomalhaut. Another dramatic example is around the star HR 8799, another young star. This coronagraph works a little bit differently, so they've subtracted off the star, which has left this bizarre mottled pattern behind. But outside of that mottled pattern, they are sensitive to three young, hot objects, three planets at very large orbital distances around this young star. And so the final method I'll only briefly touch on, because we'll hear much more about it later, is the transit method. The idea here is that you look at a particular star and you hope that it has close-in planets whose orbits are just aligned perfectly so that the planet will pass in front of the star. When it does, it will obviously block some of the light from the star, and the star will briefly appear dimmer. It'll appear dimmer for as long as the planet's in front, and it will appear dimmer every single time the planet goes around. And that's called a transit, and it's one of our most powerful ways of detecting planets, because with this method, you can actually detect how large the planet is, which, when combined with knowledge of its mass, tells you what it's made of. So let's shift gears from the diversity of ways to detect planets to the diversity of planets that we have detected. Of the normal stars that we've surveyed with the radial velocity method, which is one of our most complete ways to do this, 6% so far have detected planets. So we've found planets around 6% of the sample. That's almost certainly a lower limit. It has to be, because we're getting better at finding them, and we'll be finding more in the future. So at least 6% of stars have planets around them. Of those, about 1%, have so-called hot Jupiters. This is the name that we give these giant planets that Eric was talking about that migrate very close to the star where they might transit. So about 1% of stars seem to have, for whatever reason, giant planets like Jupiter very, very close in. And by close in, I mean much closer to their star than our planet Mercury is to the sun. They have orbits around 3 days. We also see a high degree of multiplicity. That is, about 30% of the stars that have one planet, upon further inspection, turn out to have another one at least. And we now know of systems with 3 planets, 4 planets, 5 planets, and more. So 1 in 3 stars has more than one planet. More than 1 in 3 stars with known planets has more than one. The planets that we detect have a great diversity of orbits. This is a plot showing the distance of the detected planets from their star in logarithmic units, where 1 here represents the Earth-Sun orbital distance. The first thing you notice is the so-called 3-day pileup. There are lots of planets detected close in. These are the hot Jupiters. There's a huge spike here, and that's because the transit method is most sensitive to planets down here. So we discover lots of planets close in using transits. But even if we didn't look at the transit method, we would still see a lot of planets here in this 3-day pileup. For whatever reason, planets end up here. Then there's a bit of a valley, and then we detect lots of giant planets out in orbital periods of a year or more. This is probably where these giant planets are forming. And this fall off here isn't real. We just haven't observed stars long enough to see orbital periods much longer than about 10 years. So there are certainly more planets to discover out here. We see planets around almost every kind of star we look at. So here is the histogram of the planet host stars sorted by the mass of the star. We see that most of the stars known to have planets are around the mass of the sun, but even stars much more massive than the sun and giant stars that have evolved in particular are known to host planets. There are fewer of them because it's a little harder to look there and we don't look as hard. And we also see this bump down here. These are very low mass stars. They're cool, red, small stars. The reason we like to look for planets around them is that when a planet is there, it tugs on the star harder. Or rather, the star moves harder when it's tugged upon because it's just less massive. And so it's easier to find very low mass planets around these sorts of stars. So we make special efforts to look at them. We see a diversity of masses of planets. This shows all of the planets found with their masses in Jupiter masses. So most of the planets we find typically are around 1 Jupiter mass. The bigger the planet, the easier it is to spot. And so all of these super Jupiters were basically completed. We find them all. As you get less massive than Jupiter, the detection becomes more challenging. And so we find fewer of them, not because there are fewer planets, but because they're harder to detect. We make special efforts to find very low mass planets. We're really looking for something like the Earth. And so you can see we're starting to see a new population pop up of planets like Neptune and Uranus, and perhaps soon planets the mass of the Earth, which would be just off the edge of the plot here. In addition to the diversity of planetary masses, we see a diversity of planetary sizes. Here, and Eric showed something like this, I'm showing the mass of the planet, again in Jupiter masses, versus the size of the planet, the physical size of the planet, plotted linearly. So 1 Jupiter mass and 1 Jupiter radius puts you right here, and we see plenty of planets a lot like Jupiter. We see planets more massive than Jupiter that are larger, but also planets much more massive than Jupiter that are the same size, and planets the same mass as Jupiter that are much bigger. There's not much pattern going on here. These planets come from a variety of different histories in their orbits, variety of different distances from their stars, and presumably they have a variety of different compositions. As we push down towards lower and lower planets, we are now detecting things like Neptune, presumably ice giants like Neptune. And as you can see, we're getting to rockier and smaller planets as we approach something like Earth. We refer to just about anything between Earth and Neptune here that we would discover as a super-Earth. The term super-Earth just means that the mass of the planet is more than Earth. Sometimes we'll get a little sloppy and refer to these as rocky planets. We won't really know if a planet is rocky unless we've measured its size with a transit and its density is so high, like that of the Earth, that we can be certain it is almost entirely composed of rocks and metals. So we're still looking for a certainly rocky planet or a certainly terrestrial planet. But I think that detection will be coming along just in the next few years, and Kepler will help a lot with that. And finally, I want to mention this term, the habitable zone, because we don't just want to find a terrestrial planet. We don't just want to find a terrestrial planet that is about the size of Earth. We want to find something that could potentially be an Earth twin. You could imagine that if we took the Earth and we moved it further from the sun, the oceans would freeze and we would have no more liquid water. And if we moved if we moved further from the sun, we'd freeze. If we moved closer to the sun, then the oceans would eventually boil if we got too close. If the sun were hotter and brighter, then we would have to be further away in order to have liquid water on the surface of the Earth. We define the distance from any star where a planet could potentially have water if it has a solid surface as the habitable zone around the star. So for hot stars, the green region here represents the habitable zone. The red region represents where it's too hot. The blue region is where it's just cold. So the green region is the Goldilocks region. It's the region that's just right. And depending on the size of the star, for cool stars, it's quite close. You have to huddle quite close to the star to stay warm. For the hot stars, you have to be pretty far away. So what we're looking for is a terrestrial planet, something certainly rocky, about the mass of the Earth, that orbits entirely within the so-called habitable zone. And then we will have found a potentially habitable planet that hopefully someday we can get direct images of and actually study as a near-Earth or an Earth twin. And with that, I'll pass the torch.
This program is brought to you by Caltech. Visit us at caltech.edu.